Hello everyone, welcome to the second video of the lecture series. So in this video we will solve more problems from quantum mechanics. So this is our first problem of today's lecture. So the problem states that we have a harmonic oscillator that has the following Hamiltonian. So this is a standard one-dimensional harmonic oscillator Hamiltonian. Now it is parted with a potential lambda x to the power 4. And we are given some of the matrix elements of x square in terms of its expectation value. So these are given, and as we know that n is the eigenstate of the Hamiltonian 80, so which corresponds to the eigenvalue. We know that, and as we apply this perturbation, so if we apply some perturbation, then the energy eigenvalues, so this will also be perturbed, and due to this perturbation, so there will be some correction term in the energy. So now suppose that E0 and delta E1, this denotes the energy correction of the order of lambda to the ground state and the first excited state. So then we have to calculate the fraction delta E1 by delta E0. So first we have to know a little bit about perturbation. So if we don't have the perturbation here, that lambda x to the power 4, then we have a standard harmonic oscillator Hamiltonian, which is p square by 2m plus half m omega square x square, and it will have standard energy eigenvalues of nth excited state as n plus half. Now as we apply this perturbation, so the energy eigenvalues will not be this anymore. So if due to this perturbation, this energy values will be shifted, and since we have to find the energy correction of the order of lambda, so this means we have to use first order perturbation theory. So this is a crucial point. So if we are given to calculate the energy correction of the order of lambda square, then we have to use second order perturbation theory. But since we have to find the energy correction of the order of lambda, then we will use first order perturbation theory here. So this belongs to second order perturbation theory. Now, according to the first order perturbation theory, we know that according to the perturbation theory, according to first order perturbation theory, energy correction of nth state is given by this formula. Delta En will be n, and we have the perturbation here V n. So this is our perturbation that we apply to the Hamiltonian, free Hamiltonian. So this will be the correction of nth state. So for ground state, we have the we have the perturbation as this, and for first excited state we have the perturbation as this. So we have to find these two terms, and after that we have to find the ratio delta E1 by delta E0. So this we have to calculate. So let us proceed. So here V is given as lambda x to the power 4. So we have to find these two terms, 0, x to the power 4, 0, and 1, x to the power 4, 1. So we have to use ladder operator here, otherwise this two integration will be too messy. So we know that position operator x is defined as root over h cut by 2m omega a plus a dagger, where a dagger is what? A dagger is raising operator, and a is lowering operator. So if we apply a dagger to a state n, then it will give us root over n plus 1 into n plus 1. So a dagger will raise the state n to n plus 1. And similarly, if we apply the lowering operator, it will shift the eigenstate to just its lower value. That means if we apply a to the state n, it will bring it back down to n minus 1 state. So with the help of this, so these two are very important formula to memorize. So with the help of these two things, we will calculate this term and this term. So let us proceed. So we have to find x square, x to the power 4. So first let us calculate x square. X square will be the square of this x. So it will be a plus a dagger product of a plus a dagger. So this will give us a dagger, a, and a dagger. So similarly, x to the power 4 can be written as h cut by 2m omega its square, and we will have these two terms. So we can write this as a square, and this will be a dagger. Third term will be a dagger a, and fourth term will be a dagger square, and we will have another one of this kind. So now we have to apply this to our ground state and first excited state. So now if you start doing this calculation by brute force, so it will be very tough job, very tedious job. So first you have to notice something. So first notice that all the terms that contain only a or a dagger. So terms that contain only a and a dagger, and also the terms that don't have same powers of a and a dagger. So these terms you have to notice. So these terms will be 0. So let me give you an example. So it will be clear. So suppose we have this term n a to the power 4 n. So what will it do? It will so here will be some constant factor multiplied with, so this a to the power 4, it will bring this state n to n plus 4 state. Now we know that these n states, these are orthonormal. So this term will be 0. Similarly, if you apply this will be n minus 4 because this is lowering. Similarly, if we apply the raising operator, so here will be another constant factor and it will be n plus 4. So this will similarly be 0. And similarly, if you notice some terms such as let us take a term of this type. So suppose, so in this term a has cubic power and this has 1 power 1. So basically these two don't have same power. So what will be the case? So in this case, so here will be n and we will have a square. So these two terms will first it will bring it to n plus 1, then this a will lower it to again n. So here will be a constant factor c. Suppose the constant factor is c. So these two will bring back n to n again. But now here we have a square, so it will bring this term to this state to n minus 2, and due to orthonormality this will be 0. So in this similar manner, like any other terms that don't have same power, so it will be 0. So now if we eliminate those terms that only contain a and a dagger, and also the terms that have that don't have same powers of a and a dagger, then we will have n x to the power 4 n as h cut square 4 m square omega square a dagger square plus a dagger square a square plus a dagger a dagger a dagger a other term will be a dagger a dagger, and there will be another term a dagger a dagger a, and we will have n. Rest of the terms will be of this kind, of same not of same power, or only contains this a or a dagger. So let us evaluate this. So first term will give us n plus, if you do the calculation. So this is easy. First apply, so let me do one term here. So n a square a dagger square n. So what will be the case? So first we will apply a dagger to this, and there will be a factor root over n plus 1 n a square a dagger n. A dagger, sorry, n plus 1. Now if we apply this again, so it will this will be root over n plus 2 into n plus 2. Now similarly, when we apply this term to this state, it will again give root over n plus 2 factor and bring back to the n plus 2 state to n plus 1, and when we will apply the last a, it will give us again root over n plus 1 factor, and it will bring down n plus 1 to n. So this will be n plus 1 n plus 2 n, and this is 1, so it will give us this. So let me erase this. So in the similar manner, you can calculate the rest of the terms. So here I am writing the terms. So this we are getting n plus 1 to n plus n square. So if you do simplification, then you will get 6n square plus 6n plus 3. So if we apply this to ground state, then we have the value of n to be 0. So by putting the value n 0, we will get, here will be 0, the second term will also be 0, and for third term we will have, so we are getting for the energy correction of the ground state to be this. And similarly for first excited state we will have, sorry, so this one will be 1. So for energy correction of the first excited state will be, n value will be 1, so 6 plus 3, so it will be 15 h cut square by 4 m square omega square. So our delta E0 energy correction of the ground state is lambda 3 lambda h cut square by 4 m square omega square, and energy correction of the first excited state is 15 lambda h cut square by 4 m square omega square. So the ratio of delta E1 by delta E0, it will be 5. So the answer of this delta E1 by delta E0 is 5. So in this way you can solve any perturbation problem of harmonic oscillator. So in this problem the perturbative potential involves x, but in suppose in any other problem it involves p. So in the similar manner you can expand this p in terms of raising and lowering operator, and this power term can also be different, like it can be cubic or squared. So by that way you have to construct x square or p square or p to the power 4, or you can construct any terms, and you have to keep in mind this fact that the terms that contain only the raising operator and lowering operator, if we sandwich them between n, these two same n, then it will be 0, and the powers and the terms which don't have the same power of n, a and a dagger, that will also be 0. But that is the case for only first order perturbation theory. In case of second order perturbation theory, so we have to take account of all the excited states. So for that case calculations will be tricky, will be little messy. But for fast excited states, for first order perturbation theory, this rule is it can be applied to anywhere for harmonic oscillator problem. Okay, so let's move to the second problem of this video. So here is the problem. So here we have the wave function of a particle given in a graphical manner, and we have to find the position uncertainty of the particle. So in this problem, from this graph you have to write down the wave function. So what are the steps that we will follow? So first you have to write down the wave function of the particle, and then you have to find the uncertainty in position. That means you have to find delta x, which is defined as average of x square minus x average square. So this is like general rule for uncertainty for any observable. Uncertainty is defined in this way. So a square minus a square. And how you will calculate this x and x square? So we know that average of nth moment of any observable is given by this rule. So for position we will have psi x square dx. So we have x to the power m. So this is like from minus infinity to infinity in general. So this is the formula which we will use. So if we want to calculate delta x, we will have to calculate this x psi x square dx, and we have to calculate x square average. So it will be x square psi x square dx. So we have to calculate these two terms. So let us proceed. So first we have to write down the wave function. So by looking at the picture, so let me erase this things. Yeah. So what can be the possible wave function of the particle? So we can see that the wave function is 0 for in this region the wave function is 0, and in this region and this region wave function has the value of k, because this depth is k, and for this region and this region wave function is again 0. So we can write the wave function in this manner. So first write down the value k. So it has the value k for minus a by 2. This is minus a by 2. So and this is d by 2. So we have to take in account of this part also. So it is k for minus a by 2 minus d by 2 to minus a by 2 plus d by 2. So in this region it has the value k, and now we have to write the value 0. So it is 0 for minus a by 2 plus d by 2 to, in the similar manner we can write a by 2 minus d by 2. That means in this region we have the value to be 0, and now we will have again the value k for a by 2 minus d by 2 to a by 2 plus d by 2. That means in this region we have the value of this psi to be k, and it is 0 for x greater than a by 2 plus d by 2 and x less than minus a by 2 minus d by 2. So this is our wave function, but we don't know the value of k, so we have to find the value of k. Now we know that wave function must be normalized, because the square of this wave function represents probability. Psi x square dx, it represents the probability of finding the particle. It represents the probability of finding the particle, or whatever the system it is, system between x to x plus dx. So if we integrate this from minus infinity to infinity, this probability must be 1. So from this we can calculate the value of k. So let us proceed. So we have minus infinity to infinity psi x square dx 1. So let us evaluate this. Minus a by 2 plus d by 2 minus a by 2 minus d by 2 in this region, minus a by 2 plus d by 2. In this region psi has the value k, so it will be k square dx plus, and in this region it has 0, so it will be 0, and in this region it will again have value k. So a by 2 minus d by 2, a by 2 plus d by 2. So it has again the value k. So this is 1, and in rest places the wave function is 0. So if we evaluate this integration, so first we will have this term k square minus a by 2. This is a very standard integration. A by 2 plus d by 2, d by 2 d by 2 minus a by 2 plus d by 2. This should be 1. So from this we are getting this a by 2, this a by 2 will be cancelled out, and this a by 2, this a by 2 would cancel out. So we have these 4 terms. So we have had 2d. So k has the value of root over 1 by 2d. So this is the normalization constant. So psi is 1 by root over 2d for in that 2 region. So now let us calculate x. So for to calculate x, what we have, minus infinity to infinity x psi x star psi x dx. So this is the value of x. Now let us look at this carefully. If you observe the graph, you can see that psi x, this is an even function. Even function because this is symmetric around x equal to 0. So we know from standard integration formula that minus a by 2 to a by 2, sorry, minus a to a f of x dx, it will be 0 if f is odd, and it will be 2 0 to a f of x dx if f is even. So here this whole term, this is odd function. So as this is odd function, so it will be 0. So you don't need to evaluate this integration. So these simple things you have to always keep in mind while doing calculation. If you do the calculation, you will get 0. But this will save your time in entrance examination, this small tricks. So you have to now calculate x square. So for this, you have to evaluate this integral now. Psi star x psi x dx, we have this now, and so we will have k square and minus a by 2 minus a by 2 plus d by 2, and we have x square dx, and another term we have k square, there will be x square dx, it will be a by 2 minus d by 2 to a by 2 plus d by 2. So let us evaluate this integration. So this will be k square, and we will have here 3 due to integration, and we will have x cube, that means, and let us bring out this 2 cube factor. So it will be minus a plus d, this cube, minus a minus cube, plus for the second term we will have a plus d cube minus d cube. So let us evaluate k square by 24. The first term will give us a cube plus d cube minus 3a d square plus 3a square d. Similarly, in the second term we will have like minus a cube minus d cube. So we can take this minus common, so it will be like a cube 3a square d 3a d square. Third term will be similar, so it will have a 2 factor here, and for the last term, so we are doing here plus, so d cube, it will be d cube minus a cube, and minus 3 d square a, and another term will be 3a square d. Yeah, I think this is fine. Yeah, so for this, and we will have here this a cube, and this 2a cube, it will be cancelled out. So the rest of the terms will be, we have 4d cube minus 6ad square plus 6 square d, and here we have 6 square d plus 6ad square. So these terms will also be cancelled out, and we now let us put the value of k. So it is 1 by 2d, and we have 4d from the upper portion, so we will have d square plus 3a square. Yeah, so d, and it will be 1 by 12 d square plus 3a square. So this is the value of x square. So the position uncertainty, the value will be x square, and this term is 0. So we will have root over of this term. So it is root under d square plus 3a square by 12. D square plus 3a square. Yeah. So the correct answer is this. So in this similar way, you can calculate uncertainty of any observable. So here we did for position. So similarly, you can do for momentum or any other observable. So just you have to calculate the first order moment and second order moment of the observable, and from this formula, you can get the uncertainty value. Now let us move to the third problem. So the problem states that we have a Hamiltonian for a two-level quantum system. So this is the given Hamiltonian, and the state of the system at time 0 is given. So this is the state at time 0. So we have to find this at any time t. So let us proceed. So first, let us try to look at the eigenvalue and eigenstate of this Hamiltonian. So eigenvalues are pretty straightforward. So this is already diagonalized. So this has eigenvalue E1 and E2, and if we want to calculate the eigenstates corresponding to that eigenvalue, so let us do it for E1. So for E1, suppose AB is the eigenstate, so we will have in this side, and if we calculate this, then we will get E1A is equal to E1A, and E2B is equal to E1B. Now since E1 is not equal to E2, we have to have B equal to 0. So for eigenvalue E1, we have eigenstate. So B is 0, and we can take any value of A. So let us take value of A to be 1, because we want the eigenstate to be normalized. So similarly for eigenvalue E2, you can calculate its eigenstate, and it will turns out to be 0, 1. So this is the eigenvalue and eigenstate of the Hamiltonian. So now let us write the state at time t equal to 0. So at time t equal to 0, state is given as 1 by root 2 1 1. So we can write this as 1 by root 2 1 0 plus 1 by root 2 0 1. So this is what? This is eigenstate corresponding to E1, and this is eigenstate corresponding to E2. So let us denote this by this one by 1 and this 2 by 2. So we have this state here at time t equal to 0. Now since 1 and 2 are eigenstates of this Hamiltonian, so at any later time, so at time t equal at any arbitrary time, we have psi t to be 1 by root 2 e to the power minus I e1 t by h cut 1 plus 1 by root 2 e to the power minus I e2 t by h cut into 2. So how we are writing this? Suppose we are writing this by following. So suppose we have state at time t equal to 0 as n Cn n, where this is eigenstate of the Hamiltonian. Then we can write psi t as Cn e to the power I e n t by h cut into n. So we can write this only when this n is eigenstate of the Hamiltonian. Now since 1 and 2 are eigenstate of the Hamiltonian, we can write the state at any later time as this. So what do we have to calculate? We have to calculate this term. So let us evaluate psi 0 psi t. And we have to evaluate its square. So we can write this as 1 by 4. It will be 1, 2, and here we have e to the power minus I e1 t by h cut 1 plus e to the power minus I e2 t by h cut 2. And we have its square. So from the orthonormality condition, we can write this term will be 1, the psi bracket product of 1 1, it will be 1. So we will have e to the power minus I e1 t by h cut. This term will be 0. This term will also be 0, and we will have the last term. So it will be e to the power minus I e2 t by h cut its square. So we have this one. So what we will get, the square means since it is complex number, so we have to find its mod value. So it will be like complex conjugate, like a square. So it will be a star a. So first we will have this term, and we will have this term. So let me write mod here, so it will be more clearer to you. So it will be mod. So we will have this product will be 1, this product will also be 1, and we will have one term as this e1 minus e2 t by h cut, and we will have another term e to the power minus e1 minus e2 t by h cut. So let us do a simple algebraic manipulation. So multiply this by 2, and we will have here 2. So it will be e to the power I e1 minus e2 t by h cut, and it will be minus I e1 minus e2 t by h cut. So we know that this is simple cosine function. So it is e1 minus e2 t by h cut, and we can take this 2 common. So we know that 1 plus cos theta is cos square theta by 2. So by applying this rule, we will have here cos square e1 minus e2t by 2h cut. So this is simply half cos square e1 minus e2 t by 2h cut. So let us look at, okay, so we don't need that manipulation. So yeah, option C seems to be correct. So this is our answer.